being here. Yeah, this is the title of the talk, and I think, yeah, so this is ultimately going to be a talk about connecting, well, it's a rehashing of an old story, but with a tiny twist at the end, as you'll see, connecting Gromov-Witten invariants in modular forms. And the way to maybe motivate this talk is to maybe start with the following motivating problem. So suppose I give you this classical number theory object, the so-called discriminant modular form, which is typically denoted by delta. And it's, as far as we're concerned, it's just a formal power series in the indeterminate Q. And it's defined as this infinite product. Okay. And right, so if you expand this this power series out in terms of Q, we'll get a bunch of coefficients sitting in front. And it turns out that the coefficients you get, they form an integer value function called the Ramanujan tau function. And this function has an amazing amount of arithmetic properties. Yeah, so this is the so-called Ramanujan. It's been studied ever since the time of Ramanujan, so the early 20th century. And yeah, so why should we find this function interesting? Well, yeah, so here's some results about it. I go all the way back to Mordell, and then I guess it was 1917. And then when Deligne proved the Weil conjectures, he gets the following theorem as a concept as well. So So, for example, we know that this tau function is multiplicative. In other words, if I give you a product of two numbers that are relatively prime, and it splits in this way, which, of course, just staring at this power series expansion, you wouldn't expect that, right? But that to be true due to some very deep arithmetic properties of elliptic curves. But then also, there's this, yeah, so this is more or less what Mordell did, and then in Deligne, I should say this is only true if m and n are relatively prime to each other. And then we also know that if I give you a prime p, then it turns out that if I feed a power of this prime p, I get something like this. So power p to the r minus p to the 11 power p to the r minus. And then this is for greater than 0. And furthermore, this bounded and absolute value. Okay, so this is the second part is more or less Deligne, and the first part is Mordell. So yeah, so this was at the time this was called the Ramanujan conjecture, and there's still some things we don't know about this tau function, and in particular, there's a conjecture that goes all the way back to 1947. This Lemur was thinking about this function, and he noticed that this thing always increases in absolute values. So he guessed that maybe it never vanishes. So this was one long ending problem. It's not. And so so this the first person to claim that it might be was Lemur, 1947, and this is still open. Okay, right. So far, everything I've said is this purely number theoretic setup. Okay, now right. So what if you're given if you try to compute this thing, or if you try to prove this, if you try to provide a proof to Lever's conjecture, right? One thing you might try is you might say, okay, maybe I can find a nice interpretation of the tau function, whether that's a closed formula or maybe interpret tau then as counting something, and then get non-vanishing as a consequence, right? Right. So let's see. So one possible strategy. By the way, if there are any questions, please feel free to just speak up. So one possible strategy is to reinterpret tau then via either combinatorics or very classical numbers. What do I mean by this? Well, the first person, or the first attempt at this strategy, goes all the way back to Niebuhr back in, it was 1975, and he said, actually, sorry, I got this wrong. This was before, it was the year after. So Niebuhr said, if you work really hard and you ask yourself, okay, what kind of differential equations should this thing satisfy, and do some nice arithmetic magic, then he discovered that Niebuhr said that tau then has this really nice succinct closed form expression. It goes like this. So let's see. N to the 4 sigma n 24. I'll tell you what this means in a second. Let me just write this out. Squared 35 squared 2 n. Yeah, so he found this closed form expression for the Riemann-Eban tau function. And yeah, so this sigma function is simply the sum of the divisors. Okay. And yeah, so this was already 50 years ago. People have known this for 50 years, and this still hasn't been enough to knock down Lever's conjecture yet. The main difficulty is that the arithmetic complexity of the sum of divisors function is pretty hard to pin down. Okay. And then there's another result more recently in 2017. We also Garvan and Schlosser, they find a closed form expression that is much more complicated, but is purely combinatorial. It depends only on sort of these partition statistics of the integer n. But okay, so that's one strategy. And so today, so far still number 3. What is the whole? How does it get back to geometry? The point of today's talk is that in the spirit of this strategy, it turns out that tau then can be written as a rational linear combination of Gromov-Witten invariants of a smooth elliptic curve. That's the point of today's talk. So today's talk is, I want to essentially discuss the result that says that this tau function is really a rational linear combination of Gromov-Witten invariants of a smooth elliptic curve, which I'll call E, of degree. So yeah, the degree of the Gromov-Witten invariance will be less than or equal to the tau input that you're trying to compute. Okay, so that's essentially the result I want to unravel for the rest of today. Okay, so how does this work? This time here.
So,
yeah.
So you said that Dylan also used that it's connected to elliptic curve. So is it a modular? Is it modular?
Oh yeah, sorry. Okay, yeah. Thank you. Yeah, I should mention that this guy here, this happens to be a modular form of weight 12, which I'll talk more about what this means later in the talk. But yeah, so this is a modular form of weight 12, and actually it's better than that. It's a so-called cusp form, so it has zero constant term, which means that so the dimension of cusp forms is one dimensional, so this is unique up to scaling for this vector space. And correct. So that's a great question, by the way, because that's exactly this is the observation that allows us to use Gromov-Witten stuff to talk about this stuff. Okay, so all right. So yeah, so keep that in mind that the tau function is captured by a weight 12 modular form, which I'll unravel in a second. Yeah, so let us now go to Gromov-Witten and see how we get back to that. Okay. Okay, so let's do some recollections on Gromov-Witten invariance. So Witten invariance. Smooth. Okay, so what's the setup? So again, the E will be smooth. Here. Okay. And we'll let M bar G N circ of B comma D. Will this be the moduli stack of possibly disconnected? That's what the dot means here. So possibly disconnected stable maps to the smooth elliptic curve with a genus G target and marked points of degree. Good. So that's where we want to do our intersection theory. Yeah, so the stationary descendants in the title here. So stationary.
Is that over the complex numbers?
Yes. Yeah. Oh, but then the question is, does it matter? I don't know if it actually matters. Yeah, but yeah.
I'm fine with it.
Okay. So, yeah, so with complex numbers, good. Okay, so the stationary descendant from a Witten invariance, the E are the intersection numbers. So we'll use the classic Witten notation here. So that's tau K1, different tau than that tau. Okay, it's just a silly coincidence. Okay, through tau Kn, circle E, lowercase e, and this is defined to be. So we integrate over the virtual class. This guy. And these are stationary, so along the evaluation maps, I just pull back the class of a point on E, and then I put in my usual psi classes. Those are the Gromov-Witten invariants we're interested in. Now, in general, as we enumerative geometry people know, Gromov which invariants are in general difficult to compute, right? However, by the great work of Okunkawa and Panda, these guys have a particularly nice closed form expression. So in general, these in the following set. So here is a closed form expression for all of these intersection numbers. Okay, so what is this? So this number happens to be, so I'll write it out, and then, but we'll have to talk about all the notation that shows up in it, so. Oh, maybe I should probably mention that, yeah, let me just mention that this has a virtual dimension 2G is 2. What's that? So as D varies, you get a new moduli space, but it doesn't actually contribute to the dimension, which is, as you'll see, this is a nice observation. And so, yeah, but what is this intersection number? It happens to be this. So that's 1 over product of a bunch of factorials coming from the insertions ki. Yeah. And then this purely combinatorial, which is really the part I have to kind of describe. So first of all, it's a sum over pairs of partitions, say lambda and mu of the degree d. And it goes, so I'll write this out and then I'll say exactly what each term means. Okay, so there's we have this closed form succinct expression for these which invariants. And but now I have to tell you what everything means on this board here. So is there a level where I shouldn't go below? No, okay. Okay. Yeah, so first of all, what is this number depending on the partition lambda? So Z lambda is actually a purely group theoretic quantity. It turns out to be the order of the centralizer of any element.
So this is like 2 partitions, or it's like partition in 2 terms?
Two distinct partitions of the integer D, yeah. So yeah, it's a pretty big sum for left D. So, but I mean, but we can write it down. That's the key. So so the order of the centralizer of so what you do is you take any element. You take any element in the symmetric group on D characters of cycle type lambda, and you compute its centralizer. It turns out the centralizer of such an element only depends on the cycle type. So that's why this number makes sense. Yeah, so this is in SD, where lambda is a cycle type of pi. And in fact, you can even do better. You can actually write this down even more succinctly. Or more concretely, it's this. What this means, so this is m sub I is the multiplicity of I in the partition lambda. So it's the number of times that I occurs in the partition lambda. and then lambda sub I is just the ith part of the partition lambda. Okay, that's z sub n. Good. The other part comes from this. So this is more classical representation theory of the symmetric group. Yeah, so if you know already the representation theory of SD, then you've seen this quantity before, but let me just, in case someone hasn't seen it, I'll write it out. Right, so if I give you a representation of the symmetric group, we know that such a representation is completely reducible. We'll break up into a bunch of irreducibles. The irreducible representations of SD are in bijection with partitions of D. And for every irreducible representation, I can take a character. And that's what, so in other words, take the trace of that representation. And that's what the chi lambda means. So these are the characters of the irreducible representations of nations. I'm going to call them S lambda.
So it's going to see star or is it like an operation?
Wait, it can sometimes vanish.
Okay.
Yeah, it can sometimes vanish. The trace of the representation.
Okay.
Yeah. But yeah, so you have these maps chi lambda, and when I write chi lambda mu, what I just mean is just plug in any element in SD of cycle type mu, and this by representation theory, we know this trace should be constant on conjugacy coefficients. So that's why this number. So this number makes sense. Okay, good. So that's the chi lambdas, and then finally, maybe one more thing I want to say is that even though this is coming from the representation theory of SD, I really want to stress is that these guys are purely combinatorial objects. Because, for example, if you ever need to compute these guys, there's really only two ways, one being the more popular way, which is you would have to use the so-called Murnagin-Nakayama rule. So the Murnagin-Nakayama rule is essentially a recursive way to compute these numbers. And when you look at the recursion, it really is just purely combinatorial. It's counting the number of skew tableau of a certain shape, et cetera, et cetera. So, but yeah, so to compute these characters, really, or I should say these numbers coming from the characters, this is a purely combinatorial exercise. But then I think the piece that is maybe less classical and less familiar to people is this piece here. So what is P sub k? So P sub k of lambda. Well, yeah, so lambda is a partition of D. I can just tell you what this thing is. It has a nice little form expression. It goes like this. I have to correct by something. Okay, so yeah, so this sum is just some quantity depending on the partition lambda. This is the only thing we need to know about this is a K Bernoulli number. So okay, so yeah, now you look at that and you say, where is that coming from? Well, so first of all, if you know some symmetric function theory, you look at this and you say, well, this looks awfully close to just your standard symmetric power sum function, right? But it's shifted by this minus I plus 1/2 everywhere. So yeah, so this actually I'll start erasing there. Yeah, these functions P sub k are examples of these things called shifted symmetric functions. And the theory of shifted symmetric functions goes all the way back to, oh, should I use one of these and not the other? Okay. Yeah, the theory of shifted symmetric functions goes all the way back to Okunkov, where he and Bloch proved that you get modularity by taking something called a Q bracket of functions like this. In any case, that story doesn't matter so much to this one, that one until today. But I would say that they don't come out of nowhere. That it comes from a well-developed theory that is motivated for slightly different reasons. So, okay. So, piece of case. Last thing. It's right here, actually. I have a clean board. So, these are piece of case examples of so-called shifting. And so they're shifted in the sense that they're not symmetric in the variables lambda I, but one can show, I mean, one can just clearly see that they're symmetric in the variables lambda I minus I, and that shift is where it gets. Okay, but even though you have this closed form expression, I mean, on the one hand, so yeah, you might think, okay, fine, it's distinct, but how easy are they to compute? Well, it turns out that starting from here, you can actually get a connection to modular forms. And we'll see in a second that connection to modular forms makes these numbers incredibly rigid. You can compute, you can sort of, they're very rigidly determined once you know the first few of them. So what do I mean by that? So first, so now let's jump hard into the land of modular forms for a second. Okay, so a definition slash theorem. Okay, so let's let k be some some positive even integer. We say the Eisenstein series of weight k find to be following formal power series in the Q. Okay, so that's the Eisenstein series of weight k for any even number k. And oh yeah, so what does this mean here? So sigma of k minus 1, and then is this similar to the sum of divisors, but now we just take k minus 1 powers of it. Good. So now consider the following polynomial ring. Consider, I'll call this, here I'll call this M, which is take the polynomial ring and say E4 and E6. Okay, and let's give this ring a grading by the weight. So with a homogeneous grading by let's say we'll just say the degree of E4 is 4, and the degree, or that's degree of EK is. Okay. And so when I give E4 and E6 this grading, then I can write M as this direct sum, where I only look at the degree k pieces individually. Okay, then what we'll say is that, so we say any element sitting inside the kth graded piece is going to be a modular form of weight k. F. Now, of course, if you've seen modular forms before, you know that this is an incredibly expedited version of modular forms, right? I haven't even talked about the modular group at all, but really, this is the extent of modularity that I'll need for the talk. Okay. Okay, so yeah, so a modular form of weight k is anything sitting in M sub k, and in particular, so it turns out that so as a fact. Turns out that E sub k is always modular. K at least 4, which is a fancy way of saying that there's a ton of relations of these E sub k's for higher and higher k. Right? So for example, if you look at E8, right? So E8, according to this fact, is a modular form of weight 8. But by this fact, I should say that another fact is that EK modular by k to the front, and every modular form is right. So for example, E8 is a modular form of weight 8, but of course by this fact we know that that must mean E8 is a scalar multiple of E4 squared. So you get all these sorts of relations for modular forms. Okay, good. And then similarly, for we'll define QM, which is going to be a polynomial ring in E2 and E4 and E6. Be the ring of quasi-modular forms. Yeah, so on one hand, you might say, okay, the only difference between modular and quasi-modular is I get this extra E2 sitting inside. But as far as the historical development of this field goes, the real reason why people wanted to consider this slightly larger ring is that they wanted to solve differential equations whose solutions were modular forms, but they couldn't do that because the ring of modular forms is not closed under differentiation. But it turned out that when you slightly increase the size of the ring by this much, then you do get that property instead of everything like this. So yeah, this sort of motivates the reason why people care about quasi-modular forms. Okay, so and then finally, So I'm almost getting to the connection to modular forms and chromal Witten invariance, but so let's, if I write UM as being graded by weight K quasi-modular forms, where I declared E2 to have weight 2. Okay, so these are U modular forms of weight K. Then finally say the thing that will get us to where we need to go, which is this. Again, it turns out that the reason why these guys, even though they have, you look at them, you said, they have some combinatorial complexity that look pretty hard to get your hands on. However, it turns out they have this very nice property. Right, so the theorem says that if I assemble my Gromov-Witten invariance that I wrote over there into this generating function, which I will for here on out use this notation to refer to it, it turns out this is always a quasi-modular form of weight. Yeah, let's add up ki plus 2 for all the AI is up here. Okay. So that's a very nice result, right? If you think about it. What this says is that if I really want to compute some really high degree D invariance, right? Obviously I should not resort to this. What I should do, well, I mean, I just have to do this for a few values, right? And then the quasi-modularity says, okay, if I know the first few values, I know the whole thing because the vector space of quasi-modular forms of a certain weight is a finite dimensional vector space. So I can write it out as a bunch of Eisenstein series. So okay, so that's why it's such a nice result. But in particular, it's nice because now we can talk about the motivating problem from the beginning, which is, well, I talked about this discriminant modular form. It happens to be a modular form of weight 12. So in particular, it's also a quasi-modular form of weight 12. And so now you look at this statement, look at the discriminant modular form, and you say, can I express one in terms of the other? And vice versa. Okay, good. So how do we want to do this? So let me okay. I feel like some jazz music that plays when I erase. The silence is death.
We could tell a joke, but it makes it more difficult to do the beginning of
Yes.
So in your formula there, is the n fixed? Because, I mean, or this,
Yeah, and it's fixed.
but in the product, it looks like n is growing.
Oh, sorry. Yeah. This n is different. That's it. That's yeah. Sorry about that. Okay, let me. All right.
So it should go up to the n, like the product should go up to the number of terms on the left.
No, it's just okay. Yeah, sorry.
To infinity.
A very good point. Yeah, it does go to infinity. So let me clear it up. and primes, yeah. Okay, now this is legit, okay, good. Okay.
How does the dimension of this quasi-modular forms spaces this certain way grow?
Right, yeah, so the dimension of the quasi-modular forms of weight k, I mean, it's just like it's the polynomial algebra calculation that you would do. It's the number of partitions of k with parts 2, 4, and 6. Yeah. Right. So for example, the one that we're going to care about later, the dimension of weight 12 quasi-modular forms is 7, right? Because you can explicitly write out all of the Eisenstein series that would be a basis for this. It'd be all right for us to do. E2 to the 6, E2 squared, E4 squared, and so on. And you enumerate all this to get 7. Okay, good. But now let's go back to seeing how this can be used to say something about Lieber's conjecture. So, Descendents quasi. Okay, so throughout, let's define the following. So I don't want to keep writing those out. I want to just refer to those generating functions. And so this I'll just sometimes write as t sub vector k. I'll call this a stationary descendant of weight k1 plus 2 plus and so on. The stationary descendant of k.
What exactly does stationary refer to?
Great question. Stationary refers to the fact that you're pulling back the point class on all the n evaluation maps. So it's really you're sort of virtually counting curves that are incident to you're fixing the curve to map those n mark points to some fixed endpoints on the target.
So stationary just means that you're using point conditions.
Yeah. That's all. Yeah. And then there's this other what is primary? There's other distinction primary insertions too. Yeah. So which is this? I think it's just any cohomology class will do, right?
Primary is when I think when there are no psi classes.
Good. Yeah. Exactly. Okay. So no, and then there's.
Wait, I thought the word descendant refers to psi classes.
Yeah, so descendants mean that there are psi classes, and primaries when there are no primary invariants are when there are no psi classes.
Primary is not descendant. Okay.
Yeah.
Okay.
Okay. So we'll call this a stationary descendant of weight k. Where k is the sum. And I'm going to define, so m sub k, so this is going to be defined, yeah, and this is just, I'm gonna introduce this matroid, which essentially will just make the statement of certain results more cleaner in a second, but the m sub k is going to be the linear realizable matroid whose ground set is, always call it e sub k. And it's just literally all the stationary descendants of weight k. That's the ground set.
This is again notational overload of the Einstein series.
What about that? Oh, dang. Okay. Yes. Yeah, because this is like the standard matroid literature notation for ground sets. Anyways, sorry about that. I mean, but if there's any confusion, I'll always clear it up. Okay, but this is what I mean by k tilde. And yeah, so this is it's the matroid whose ground set is this, and whose bases are the collections of the bases of the finite dimensional vector space QMK, where these things actually live. Okay, good. Oh, and then finally, one last thing. S superscript k is going to be the stationary descendants of weight k, such that all of the insertions of the taus are strictly positive. We'll see why these come up in a second. Good. All right. So now, okay. So you have this theorem that says, hey, we live in the world of quasi-modular forms using just Gromov-Witten invariance. So the first question you might ask is, well, can I get every single quasi-modular form just from stationary descendants? And the answer is yes. So let's it's not at 3:30, right? Okay. It is. So let's let this be any simple stationary descendants of weights 2, 4, and 6 respectively. Okay, I don't want to keep writing this out, so let's call this A, B, and C. Okay. Then with any triple you choose, get the entire ring, quasi-modular groups. Okay, so I mean, the thing is, like, this is just a computation, right? I mean, there's only finitely many ways to choose this triple, and so then what it has to do is simply so just check the finitely many triples, and then it's a computation to check that every triple you use, you can generate E2, E4, and E6. Once you do that, you're done. Okay.
So just one question.
Yeah.
So the elliptic curve E and the degree D, they are now fixed, right? Like when
D
because you drop the
vary in this generating function.
Yeah. So the point of brackets without decoration is the generation function as fixed.
Exactly. Yeah. Exactly. Yeah.
But E is fixed.
E is fixed.
Okay.
I mean, E is just any smooth elliptic curve, right? Like we can do Gromov in theory, it's a deformation invariant, right? So pick any Wire stress equation and you can change it a little bit, you'll still get the same answer. Okay, yeah. Yeah. Okay, good. Now, okay, but now let's actually see this in action. So for example, I can choose the following triple. So I can generate the entire ring of quasi-modular forms using these stationary descendants. Say the generating function with the insertion tau 0 squared, and tau 0 cubed. Okay. And so in particular, since you know that in particular the discriminant modular form is a weight 12 modular form, and in particular it's quasi-modular. So I should be able to write the discriminant modular form as a polynomial in the stationary descendants. And in fact, this implies that I can write the discriminant modular form as a rational linear combination of aijk. So the I squared the j and tau 0 cubed to the k, where, and it's the sum where all of these are contributing weight 12, right? So it'll be 2, you sum over all ijk's, such that 2i plus 4j plus 6k is 12. Okay, and these aijk's, here they are. Yeah. Yeah, it's nice. Here's this. So in particular, this happens to be an integral linear combination in this case. Okay, and of course, if you stare at that and and then you plug in these numbers into that expression and you unravel everything, you will have discovered, yeah, a closed form expression for the Ramanujan tau function in terms of this Gromov-Witten invariant. However, it's awfully complicated, right? Because when you try to extract the degree D coefficient, you have these infinite powers, right? And you have to do something about that. Yeah. So okay, so that's one way to do it. But you'll notice that the problem, yeah, so extracting the Ramanujan tau function from an expression like that becomes difficult because of you end up getting powers of this guy. And that is simply the fact that we're expressing the discriminant modular form in a non-linear way with the stationary descendants, right? Yeah. We're expressing it as monomials in stationary descendants. And so the next question you might ask is, well, can I really stick to matroid? Can I really do everything linearly? And so the question what I'm really trying to say is that, is it true? So can we generate the quasi-modular forms of weight k linearly in the stationary descendants? And that's actually conjecture. That's I've corroborated a lot on the computer, but it's basically so the span of the stationary descendants of weight k in every example computed so far happens to be the entire ring of weight k quasi. Okay, and so I don't know if this result is true for general k, but in the case we're concerned about, it's certainly true for k equals 12, and that's the part that I care about. So let's see, 5 minutes left. Let me finish my talk with sort of the punchline here.
Jazz music.
Thank you, thank you.
How did you compute these coefficients?
Yeah, just, okay, you're talking about these ones here?
Yeah, the ones you need to express delta in terms of these stationary descendants.
Yeah, I mean, it turns out just being linear algebra, right? Because, so what you do is you say, okay, these are the unknown coefficients, right? You know that delta is a weight 12 modular form. And so, first of all, we actually know a closed form expression for this in terms of Eisenstein. It's something like 8,000 E4 cubed minus 147 E6 squared. Okay, and so what you're doing is you just say, how do I change, how do I do a change of basis? Yeah, between the weight 12 monomials that generate the weight 12 guys here and the weight 12 monomials in Eisenstein. It's a purely linear algebra exercise. What is the change of basis from one to the other?
So do you have expressions for the for like the products of these? Yeah.
In terms of Eisenstein?
Yeah.
In principle, yeah, you could. Oh, but you're saying in terms of what they are, in terms of the I, J, and K?
Well, I mean, I guess so. These things, they live in a vector space of dimension 7.
Yeah.
And you have basis in terms of Eisenstein series, and you gave me the delta in terms of the Eisenstein series. So now if you want to do a change of basis, you have to know what are the other guys in terms of Eisenstein series.
Yes, exactly. Yeah. And what you can do, what you can compute by hand, because
By hand.
by hand. you can do that because you know the first several coefficients of each of these guys, right? And so when you try to write this in terms of Eisenstein, then you have to match up the first few coefficients, in this case, the first 7 coefficients, right? That gives you a 7 by 7 linear system to solve, and you know it's solvable because it should be expressible in a unique way in Eisenstein. Yeah. Does that make sense? Yeah. Yeah, really the computation of all this stuff is just pure linear algebra. But I think what's fun is that really, as you'll see in a second, in the end, you get to say that Lemur's conjecture is equivalent to essentially this very purely combinatorial sentence involving Gromov invariance. Which yeah, okay, so the quip is that I turn a hard number theory problem into a much harder combinatorial problem. Okay, that is life, and sometimes maybe it's not much harder. We'll find out. Only time will tell. So, okay, let's finish up. Okay, so the last thing I want to say is that the previous conjecture is true for A equals 12. Okay, and the previous conjecture for K equals 12. So in particular, I know that all the weight 12 stationary descendants will generate the entire ring. So this is, I know that span these guys. Equal to this. But there's a lot of these, actually. If you sit down and you enumerate all of the weight 12 stationary descendants, there's 21 of them, right? So it's the kernel of this thing is very large, right? But it turns out, however, you can actually say something a little bit slightly more refined, which is that if you take the matroid MK or M12 in this case, and you throw away any descendants with tau zero insertion. So in other words, restrict your matroid to that minor. Then you get a uniform matrix. So in other words, this restriction is sort of will give you what you sort of generically expect for a random vector configuration, in this case Q7, right? But once you know this, what this means is that, so in particular, let's consider, right, so that means that since I'm in a uniform matroid case, any collection of 7 stationary descendants without a tau zero insertion will give me a basis. And almost done. Consider the basis B given by this. Okay, so a collection of 7 stationary descendants with no tau zero insertion. Since I'm a uniform matrix, I'm for sure a basis. Then I know that. So it turns out that means I can write delta, my discriminant modular form, as a rational linear combination of these guys. But if I want to just deal with integers for the sake of presenting it, it turns out that. That I can write a scaling of my discriminant modular form as this linear combination of these stationary descendants here, where these V's are written in advance, so they're over there. Okay, so they're pretty hard. But the fact of the matter is, the final thing I'll end with, the punchline is, that Lemur's conjecture equivalent to saying that the following alternating sum of Fermat-Witten invariants never vanishes. So there it is. So basically, what I'm saying is that Lemur's conjecture is true if and only if this generating function has the same property as coefficients never vanish, which is the same as saying this very simple statement here, because this number, this summation term shows up simply by virtue of the fact that this has the expression. But of course, this was just one basis. We could have chosen any basis. That's really, so this is kind of the tip of the iceberg. And right now, it's sort of unclear how to organize all of this linear algebraic information to tell one concrete story. But here it is. I mean, that's the punchline, I promise. Lemur, this number theory problem comes down to showing that this alternating sum of Fermat-Witten invariants can never be zero. So, okay, that's all I want to say. Thank you.